In this second video of enthalpy changes, we're going to focus on calorimetry, which is the experimental practical way of working out some enthalpy changes. This is different to the other two subtopics where we calculate indirectly theoretical values of enthalpy changes for different reactions, whereas calorimetry is a direct experimental way of working out the enthalpy change for some reactions. Before we do that, we're going to look at enthalpy profile diagrams very briefly again and look at how we can use these diagrams to work out unknown enthalpy values and also activation energy. Here's the enthalpy profile for the Haber process, and we're drawing it for the forward reaction, starting with nitrogen and hydrogen to give us ammonia. We're given the enthalpy of reaction for this equation, which is also shown here in the enthalpy profile. As a side note, you can use this value to work out enthalpy formation of ammonia, which will be different to this value. So think about how you would do that. Going back to this diagram, we notice that here's the activation energy for the forward reaction. So this is the energy put in to break the bonds and form the activated complex or the intermediates in the reaction. And this is the enthalpy change when the new bonds are formed. So this is the energy release when we form new bonds. This is the overall enthalpy change of the reaction, which is 92 kilojoules per mole. We're given the activation energy as this value. Now from these two values, we can actually work out this value here. This value here is actually the activation energy for the reverse reaction, and I'll show you this on the next diagram. At the bottom here, we've got the enthalpy profile for the reverse reaction, where we've got the ammonia as the reactant and the nitrogen, hydrogen as the products. This is an endothermic process. You can see the arrow is pointing in the same direction as the axis, so this has a positive value. Whereas the enthalpy profile for the exothermic reaction, the arrow for the enthalpy change is pointing away from the direction of the axis, so this is a negative value for enthalpy change. As we said earlier in the previous diagram, this would be the activation energy for the reverse reaction, which you can see here. So we start off with ammonia here as the reactant. We put energy in to break the bonds in the ammonia and form the activated complex. And this is the energy release when the new bonds are formed to make the products. We can use energy profile diagrams to work out unknown values if we're given known values elsewhere in the diagram. For example, we can work out this activation energy using these two values, and you can see in the diagram that the sum of these two values, ignoring the signs, will give us this value because the height of this value is the same as that added to that. So if we add these two values ignoring the signs, we should have the value of the activation energy. And all we do, because we know this is a positive value because the arrow is pointing in the same direction as the axis, the activation energy will be positive as well. Using a calculator, we can work out this value as 342. So this value here is 342 kilojoules per mole. Having recapped enthalpy profiles, we're going to move on to calorimetry, where we're going to look at different experiments to measure different types of enthalpy changes. And we're also going to introduce the definition for enthalpy neutralization. We're going to look at how the temperature changes in these reactions can be used in an equation to work out the quantity of heat that caused that temperature rise or temperature drop. We then use this quantity of heat in another equation to work out enthalpy change. And we do that using the moles of the reactant that has been used, or in the case of enthalpy neutralization, the moles of water that has been generated. The word calorimetry literally means heat measure, and it's the name given to experiments where we measure heat of a reaction directly. And there are a number of different ways of doing this depending on the reaction. The two different ways we're going to look at today are combustion of a fuel, and the second one is a reaction in a solution. So when we look at the reaction in solution, we're going to look at also the enthalpy of neutralization because that involves solutions. So when we get to that part, we're going to look at what enthalpy of neutralization is and look at this definition. In the calorimetry experiment to measure the heat of combustion or enthalpy combustion of a fuel, we measure the mass of the fuel we're going to burn at the start of the experiment. We then burn it and transfer the heat into something we can measure the temperature rise of, and then we use a small calculation to work out how much heat has gone into the substance we're heating. In most cases, at A level, we use water to be the substance that we heat, but it doesn't have to be water, it could be anything that we can heat up and measure the temperature rise of. We then put out the flame and measure the mass of the container with the fuel at the end to work out how much fuel is burnt. So we then work out the moles of the fuel burnt, and we've got the value of heat that's gone into the water, and then we divide the value of heat, which is in kilojoules, by the moles of the fuel burnt. So we then have the enthalpy change of combustion of the fuel, which would be in kilojoules per mole. So to work out the enthalpy of combustion of the fuel using calorimetry, we first of all work out the amount of heat that's released by the fuel that's gone into the water, and we can do that using an equation here, which I'll look at in a minute. And then we work out how much fuel is burnt and convert it to moles. The heat that we worked out that's gone into the water divided by the moles of the fuel burnt will give us the enthalpy of combustion of the fuel. To work out the heat that's gone into the water, we use this equation where delta T is the temperature rise of the water and M is the mass of the water. C is the specific heat capacity of the water, and this has a value of 4.18 joules per Kelvin per gram. What that really means is that I need 4.18 joules of energy to raise 1 gram of water by 1 Kelvin or 1 degree C, because an increase in 1 degree C is the same as an increase in 1 Kelvin. So for example, if I had 100 grams of water and we raised the temperature of that water by 10 degrees C, the amount of energy needed would be 100 times 10 times 4.18. So that would be 4,180 joules. So we often use kilojoules in enthalpy of combustion or NP values. So we need to divide that value in joules by 1,000 to convert to kilojoules. And often people forget to do that. Now that we've got the quantity of heat that's gone into the water from burning the fuel, we need to work out how much fuel is burnt and convert it to moles, and then divide the quantity of heat by moles to give us the enthalpy of combustion of the fuel. So once we divided the quantity of heat that's gone into the water by the moles of the fuel burnt, we must remember to put a minus sign in front of it, as enthalpy of combustion are exothermic values. So we must have a negative value for enthalpy of combustion. The most common mistakes people make when they calculate enthalpy of combustion using calorimetry is that they mix up the mass of the fuel burnt with the mass of the substance being heated. So the mass of the fuel burnt is used at the end and the second step on the calculation, whereas the mass of the thing that's been heated, which is usually water, is used in Q equals mc delta T. So this mass here is the mass of the substance being heated, and the mass of the fuel being burnt is used to work out the moles of the fuel to give us the quantity of heat per mole. So sometimes people use the mass of the fuel being burnt in this equation by mistake, and that's a very, very common mistake. So make sure you don't mix those two up. The second most common mistake people make in calculating enthalpy of combustion using calorimetry is forgetting to convert joules to kilojoules from Q equals mc delta T, because the value of Q is in joules, because the specific capacity of the water or the substance being heated up is often in joules per gram per Kelvin. So this value calculated from the equation of Q would be in joules. We normally have enthalpy of combustion in kilojoules per mole, so we need to convert this joules to kilojoules by dividing by 1,000, then convert it to kilojoules, then divide by moles to give us the enthalpy of combustion in kilojoules per mole. The last thing we're going to look at about enthalpy of combustion values using calorimetry before we move on to looking at enthalpy of neutralization and other reactions in solutions are the assumptions used when we calculate the enthalpy of combustion using these experimental setups. So one of the major problems with this experimental setup is that a lot of the heat from burning the fuel doesn't actually transfer into the water or the substance being heated that we measure the temperature rise of. A lot of it can be lost into the surroundings, into the atmosphere. So there's a huge amount of error in this experiment from the heat loss transferred to the surroundings. Some of the heat also heats up the container, the calorimeter, which is often a conductive metal like copper. That heat then can radiate away from the container and we get more heat loss that way. So to reduce the amount of heat loss, we use these draft excluders or draft shields around the calorimeter and the spirit burner, and that hopefully reflects the heat back into heating the water within the container, within the metal calorimeter. Another way to prevent heat loss from the heated water is put a lid on the water, and that also reduces evaporation, which can cause a problem in the calculation, because if we have loss of the water, the mass of the water actually decreases and the temperature rise will be bigger than we expect. The problem with evaporation doesn't just involve water. Fuel can also evaporate. If it's a very volatile fuel, we have loss of fuel from it evaporating during the experiment. So when we reweigh the mass of the fuel at the end of the experiment, we may think we burnt more fuel than we have. That means when we calculate delta H using Q over moles, the value of the moles will be bigger than it should be, and therefore the enthalpy of combustion will be smaller than it should be. While we're on this page and we can see this equation, if water evaporates from the calorimetry experiment, then delta T will be bigger because there's less water to heat, and that leads to Q being bigger as well. That will also mean enthalpy combustion calculated from this bigger value of Q will be bigger as well. So we have a problem with loss of heat from the combustion of the fuel going into the atmosphere rather than heating the substance that we want to measure the temperature rise of. We also have a problem with some of the fuel evaporating or some of the water evaporating in the experiments that will affect our calculation of delta H. On top of that, we have the fact that some of the fuel may not undergo complete combustion, and if the fuel doesn't undergo complete combustion, there'll be less heat given off through incomplete combustion, so the value of Q will be less than it should be, so that will affect our enthalpy combustion calculation as well. So we covered so far how to calculate enthalpy combustion using calorimetry and looked at these equations in the process. We also looked at how the calorimetry experiment has limitations. We're now going to look at what enthalpy of neutralization is and how to work this out from calorimetry experiments, as well as other enthalpy changes that involve the reactions of solutions. Before we look at how we can work out the enthalpy of neutralization using calorimetry experiments, we're going to define what enthalpy neutralization means. Enthalpy neutralization is the enthalpy change when 1 mole of water is formed from the reaction of an acid and alkali. So here I've written the equation to show the enthalpy neutralization of sulfuric acid and sodium hydroxide. I've written it here to balance for 1 mole of water, as this would show the equation for enthalpy neutralization because it's showing the formation of 1 mole of water. We could have written the reaction this way as a balanced equation, but it's not balanced for 1 mole of water, so this equation would not be considered to show the enthalpy neutralization for the sulfuric acid and sodium hydroxide, and the value of this enthalpy change is the enthalpy of reaction, so it's the enthalpy change for this equation written as it is, and it would be double the value of the enthalpy of neutralization for the sulfuric acid and sodium hydroxide, as you can see here. So here's another example of an equation written in the format to show the enthalpy neutralization of an acid and alkali, because I've balanced this to form 1 mole of water. This time I've got a different acid and different alkali, and they're both strong acids and strong alkalis. And you notice the value is the same as the other acid and alkali, which are also strong acids and alkalis. And the reason is the reactions are identical, because the spectator ions which are not involved in the reaction would cancel out in the equation, and the only things that are producing the heat are the hydrogen ions and the hydroxyl ions combining in the neutralization. So you can see I've written down the ionic equations for both of these neutralization reactions. So for example, if we look at the top one here, half a mole of sulfuric acid gives us 1 mole of hydrogen ions and half a mole of sulfate ions. Remember, this isn't half an ion, this is half a mole of sulfate. And I've written the ions out for the rest of the equations. We can then cancel out the spectator ions. So for the top one, we cancel out the sulfates, we cancel out the sodiums. The bottom one, we can cancel out the chlorides. and cancel out the calcium ions. And you can see that we get the same equation because at the top we got 1 mole of H plus ions with 1 mole of hydroxyl ions give us 1 mole of water, and the bottom one is the same. So the reactions are identical. So this is why the value of NP neutralizations for both of the reactions are the same. So now we know what NP neutralization is, we can look at how we can use calorimetry to calculate the NP neutralization by measuring the temperature rise of the acid and alkali mixed together and using Q equals mc delta T to calculate the heat change. And then we divide by the moles of water formed to give us NP neutralization, because by definition, NP neutralization is worked out for every mole of water formed. We can also use this type of apparatus to work out the NP changes for other reactions in solutions other than neutralization reactions. To work out the NP neutralization using calorimetry, we use an insulating cup, like a polystyrene cup. Some people use 2 cups inserted into one another to give doubled insulation, and then you place the cup into a beaker to make it a bit more stable on a bench so it doesn't topple over. We have a lid again to reduce heat loss, and the stirrers to ensure that the heat is distributed evenly in the reaction mixture. So this time we're not producing heat in the reaction and then transferring it into another substance like water to heat it. This time we're measuring the reaction mixture itself directly, and the heat produced by the reaction is going into the mixture itself. So we need to make some assumptions into how to work out Q using Q as mc delta T. So the first assumption we're going to make is that the density of the solution at the end of the reaction is the same as that for water. And we need to make that assumption in order to calculate the mass of the thing that's been heated up, which is actually the mixture itself. So unless we know the exact density of the solution, we can't work out the mass, and therefore we can't work out Q. And it's unlikely that we know the density of this solution, so we make that assumption. The other assumption we're going to make is that the mixture at the end has the same specific capacity as water, because we don't know the actual specific capacity of the mixture, because we have other things in it like the salt and any unreacted acid or alkali. So when we do the calculations from the experiments, we use the temperature rise of the mixture after mixing the acid and alkali. We then use the specific capacity of water, because we're going to assume that this has the same specific capacity as the water, even though it isn't pure water. You have salt and unreacted reactants in there. We then use the mass of the solution to be the same as if it was water. So we're going to assume that this has the same density as water. So if we have 100 centimeter cube of this would be 100 grams of the solution, and we use that mass then in this equation. So with the mass and the specific capacity and the temperature rise, we're going to work out Q, or the quantity of heat that has been produced. We then look at the moles of water formed in the neutralization by looking at the stoichiometry of the equation and work out which is the limiting factor in the reaction by working out the moles of the acid and the moles of the alkaline used. And the limiting factor will limit the amount of water that's produced. And this is the moles of water that we need to calculate in order to work out the value of moles here. So the NP of neutralization would be the quantity of heat calculated by this equation in the reaction divided by the number of moles of the water produced in the combination of moles of acid and alkali, taking consideration of the limiting factor of the two, which will limit the amount of moles of water produced. We divide then the Q by moles to give us the NP of neutralization, and hopefully we'll remember to convert Q, which is in joules, to kilojoules first to give the enthalpy of neutralization in kilojoules per mole. So to work out NP neutralization, we use Q from Q equals mc delta T, and then we use moles of the water produced by looking at the stoichiometry and the moles of the acid and alkaline produced, and then considering the limiting factor, we can work out the water produced in the neutralization. As I said, we can use the same equipment for other reactions involving solutions. So in that case, the moles that we're going to use is not moles of water produced, because it may not be a neutralization. It'll be moles of the limiting factor of the reactants involved. Finally, before we finish the video, we're going to look at the best way to work out delta T when mixing solutions in calorimetry, and this is done by plotting a graph. So let's assume we got an alkali in a polystyrene cup, our insulating cup, and we're adding acid to it. Before the acid is added to the alkali, the temperature of the alkali in the cup will be measured for several minutes for it to set up room temperature. And then we mix the acid to the alkali, but we don't take a reading. So here you can see that on the 5th minute where we mix the two solutions, there's no reading. And then we take readings after that. So here we've got readings for 6, 7, 8 and so on minutes. What we do then, we draw a best fit line to fit the points at the beginning, and then we draw a best fit line to fit the points near the end. And we extrapolate those lines beyond those plots towards the 5th minute. And we draw a vertical line at the 5th minute where we mix the solutions. So we use the graph to work out the temperature rise, and that will be delta T, which will be at this point to this point. So in this video we covered how we can work out NP combustion and NP neutralization, as well as other NP changes involving solutions using calorimetry. We also looked at the limitations of these experiments. So for example, there's a lot of heat loss in using a simple calorimeter for working out NP combustion, and there are things that we can do about this which I haven't covered in this video. So one of the things you can use is what's called a bomb calorimeter, which you can read about for yourself. I'm not going to cover that in this video. For NP neutralization, the assumptions we make to work out Q will limit the accuracy of the values calculated, because the mass we're using isn't really the mass of the solution, because we don't take into account there are ions in the solution, as we make the assumption that the solution is the same as pure water. Same with the fact that we're using the specific capacity of the water rather than the actual solution to calculate Q.